This is Mr. Markarian reporting from his secret lair in Madeira. This video will be about electron configuration, a topic we've been discussing in class. It can be a difficult topic for students. We're going to try to clarify some of the misunderstandings and make this easy for you guys so it's not a difficult task. So sit back and enjoy as I try to make this a little bit simpler and easier for you guys so you can understand electron configuration. Okay, what you see here is the Bohr model of the element chlorine. So this is chlorine. Chlorine has 17 protons, which are shown here in the nucleus, with 35 neutrons. It also has 17 electrons, and those are spread out throughout each of these rings, which you guys know now represent energy levels. These are what you drew in 8th grade in biology. We use them occasionally in chemistry still, but we need a more detailed model of the atom. The current model of the atom, the wave model, does not fit the Bohr model of the atom. They are not compatible in many cases, and we'll talk about a lot of that in class and why that's true. The purpose of this video is to take this model and show you what it's really like according to the wave model. In reality, what we see are atomic orbitals, and atomic orbitals, like you see here, there are many different shapes. Each of these orbitals contains 2 electrons when full. That is all they can hold. So we've got the S-shaped cloud, which is a sphere shape. We've got the P-shaped cloud, which we say is dumbbell shape or peanut shaped. We've got the d orbitals. There's 5 different kinds of those, and here we have the f orbitals, the green guys here. And so in reality, 2 electrons can be held in this f orbital, this f orbital. Each of these guys, this d orbital, they only hold 2 electrons. Orbitals are the smallest unit of the level. So how is the atom broken down? Well, the principal energy levels, which we usually call N, this equals the level. These were the rings that you drew in the Bohr model. And the Bohr model that we looked at for chlorine, those would be the rings around the nucleus. Those are the levels, the principal energy levels. Consequently, those are broken up into sublevels. And there are 7 levels possible for an element. Those sublevels are broken up into 4 different types, and those are broken up into orbitals. And so this is the hierarchy that we have going from level to sublevel to orbital. So if an element is level 1 and it has an S-shaped cloud, we would say that's 1s. Now the S in this case would be the shape, which would include in this case the sublevel and the orbital. S clouds, as you saw previously in the video, are sphere shaped, and there's only 1 of them per level. So only 2 electrons are in an S cloud in any of the 7 levels at any time. So there's a 1s, a 2s, a 3s, a 4s, a 5s, a 6s, and a 7s orbital, depending on the size of the atom. As you get into the larger atoms like francium, that would end in level 7. That is one of the larger elements on the table. So this is how the atom is split up. It's not just levels. It's broken up into sublevels and orbitals. Each orbital can hold, as we said, 2 electrons. So this is known as an orbital diagram, and this one's vertically oriented, and it shows increasing energy as we go up the diagram. So we start down here at the lowest energy, we go up, energy is increasing. Each of these lines, or sometimes you'll see them as boxes, represents 1 orbital. So you notice the 1s has a single orbital in it. The 2s, which is shown here, has a single orbital. When you get to the p's, they have 3 orbitals. When you get to the d sublevels, they contain 5 orbitals. So this is really important when we're writing out electron configuration. As we do that, what we'll usually do is use arrows to represent electrons. And you'll usually see it as a half arrow, either up or down or both. And these would represent 2 electrons. Now, the rules are in your notes. One of the rules is that electrons must have opposite spin from each other, and we talked about this in class. So if you have questions about that, see me. But each electron must have an opposite spin. There's an up spin and a down spin for electrons, and the reasoning for the opposite spin is so they don't repel away from each other and out of the orbital. So when we go to fill in an orbital diagram like this, whether it's lines or boxes, it doesn't matter. We use the arrows for the electrons. So if we were going to do the orbital diagram for hydrogen, the first electron, according to the off-bow principle, must go in the lowest level. So the first electron would go there, and in that case we would have hydrogen. The second electron also goes in there. That one has the opposite spin, and now we have helium. The electrons keep adding in. We go to 2s. Now that is a 2s1. No longer helium. Now we have lithium. The next one to fill in is a downspin for the 2s. That would give us beryllium. The next electrons going in would be the 2p1, then the 2p2, and then the 2p3. Now this is according to the 3 rules of Aufbau, Hund's, and the Pauli principle. The electrons have to be spread out before you can start filling them in again. At this point we have nitrogen as our element. The next electron would go in, then the next one, and then the last one. Okay, commonly the orbital diagrams are shown horizontally instead of vertically. So if we put in the electrons, we have 1 here, 2 goes there. Right now we have helium. We go into the 2s, we'd have 2s1, 2s2, and if we stop there at 2p1, we have 1, 2, 3, 4, 5 electrons. If it's neutral, which we assume it is right now, that's 5 protons. And if you look that up on the periodic table, you guys know 5 protons is boron, which is the letter B or the symbol B on the periodic table. So often we do that horizontally. Now, here's where electron configuration comes in. Orbital diagrams are great, and it does show the electrons and the spins and everything like that. The electron configuration is a shorthand of this, and it's really easy. So for boron, instead of doing the box that you see here, or doing a line with the arrows, all I would write is we've got 1s, and it has 2 electrons, so we write it as 1s2. Then we would transfer this portion down. That's 2s, and it has 2 electrons. So it's 2s2. We look at this portion, it's a 2p, and it has 1 electron. So it's 1s2, 2s2, 2p1. That's the code for boron. No other element has that code. No other atom has that code. Boron only has that electron configuration in atomic form. And so as you add in electrons, you keep adding to that. Now, the hard part becomes, usually for students, they'll say, well, I've got to memorize everything up to the end of the periodic table. Well, that's not true. The periodic table is set up so you don't have to remember anything as far as the order in which they fill. The periodic table gives it away. So let me show that to you. So if you look at the periodic table is set up in such a way that you can remember the electron configuration if you remember the different parts of the table. And so we've got a couple of things to remember here. The S's are in the tall tower over here. The P's are off to the right in the other wider tower. The D's are here in the center, and the F's are here at the bottom. And the F's actually fit up right in there. So when doing electron configuration, you can figure out the order just by looking at a periodic table. So let me explain what I mean by that. For the element hydrogen, hydrogen is here it only has one electron, so we would say that it's 1s1. If we cut across to the second box, that's helium, that is the second electron. This would change to 1s2. I drop down to the next one. The next thing that fills up is 2s1, 2s2. Now we're at element Be, which is beryllium. I go across reading like a book from left to right. The next thing to fill up is the 2p. Notice there are 1, 2, 3, 4, 5, 6 boxes. The p's, as you guys know now, can hold 6 electrons. By the time I get to the end of this row, we're at element neon, which has a total of 10 electrons. I keep dropping down in order. The next thing to fill up is 3s2, then 3p6, 4s2, and then here we get that drop, the 3d drop. And so those electrons are coming in at a lower level, but they're coming in after the 4s. After 3d is the 4p, then the 5s, then the 4d, then the 5p, then the 6s, and this is where the f's come in. The f's come in here. 4f would come after 6s, and then it would be 5d. Now, again, with the d's here, you notice there's 10 boxes, so that would be 5d10 by the time you get to there. Then 6p6, then 7s2, and then the 5f comes in to that spot, and then 6d, whatever we have, 6d3. The table actually goes further than that, all the way out to here, and we'll look at some of those in class. So this diagram here is again of the periodic table. The person that put this together put helium over here in this spot. They did it because it makes a little more sense because you have 1s1, 1s2 there. It can go over there. Sometimes some periodic tables have it over here. Sometimes they have it over here. This shows you what each element ends in. So if you have Fr, francium, that electron configuration will end in 7s1. If you have the element above it, cesium, it ends in 6s1, and so on. If you have, let's see, we've got neon over here, that ends in 2p6. By the way, that is the only element that ends in 2p6 in its atomic state. And so this is a great table to kind of see where they all end up when you're done with the configuration. Okay, so that brings us to the last topic, which is the abbreviated version of the electron configuration. So let's say that you wanted to write the configuration for, let's see, we have hydrogen, lithium, sodium. Let's say we wanted to write it for potassium, which we have right there. Potassium ends in 4s1. To do the abbreviated, I just go back to the noble gas that is before it, and in this case we have neon up here and then argon. So instead of writing all of the 1s2, 2s2, 2p6, 3s2, 3p6, all of that can be illustrated or shown with a brackets AR, and then I plug in 4s1. If we're doing an element that's down here like zinc that ends in 3d10, I would do the argon in brackets because that's the noble gas before this one, and then I would put in 4s2 because that's filled, and then I would count off 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that one would be 3d10, and this would represent zinc. So that is the short version. I'll call it the abbreviated version. Both are acceptable. During your test for this stuff, I'll have you doing both. I think you should have to be able to do both of these things to be successful. But after this unit's over, most of the time I'll just write it like that in the short version. So that's electron configuration. I hope that cleared up things a little bit, or at least gave you some more examples of how to write these, how to do the abbreviated, and especially how to read the periodic table so you don't have to memorize this stuff. There's no reason for memorizing the order in which they fill when the periodic table gives it all away. So enjoy, keep working at this stuff, come in and get help if you need it, and I'll see you in class.